Okay, moving on to Chapter 10. Chapters 10, 11, and 12 are all going to focus on a branch of chemistry that we call organic chemistry. What you have been working on, chapters 1 through 9, is what we call inorganic chemistry. In my opinion, organic chemistry takes a little bit of a different slant in your study skills. Chapters 1 through 9, we dealt quite a bit with math. And in organic chemistry, you won't see much math. I think, personally, if you have never been a note card student, this might be the time to go buy a pack of note cards, because organic chemistry does have a lot of just rote memorization in it. So organic compounds. Organic compounds used to be defined as any molecule that contains carbon and was derived from a living or once living organism. Nowadays, the modern definition ignores its source, so where it came from. We don't care if it comes from a living organism. It's just mainly focused on molecules that contain carbon. Carbon is the base. But then we have to exclude some of these inorganic compounds that contain carbon. So carbon monoxide and carbon dioxide are not considered organic. The carbides, which is when you see carbon bonded to a metal, that's not organic. And any of your carbonates. So if you remember your polyatomic ions, we had carbonate and the bicarbonate ion. So if you ever see a metal to the carbonate ion or a metal to bicarbonate, those are not considered organic. Other than that, most of the molecules you see that have carbon in it are going to be considered organic molecules. They're also going to contain a lot of hydrogens. So when you see a molecule that's got a lot of carbons and a lot of hydrogens, that's going to be a giveaway that it's usually organic. So by default, your inorganic compounds are just all the compounds that are not organic. So if you decide it's not organic, then it means it's inorganic. So I'm going to want you guys to be able to identify the difference, be able to tell me whether it's an organic molecule or an inorganic molecule. So here are some examples. Here's propane, which has the formula CH3H8. It's an organic compound that's used for fuel, so I think we're familiar with it when we have barbecues. An example of an inorganic compound is going to be sodium chloride. So remember we talked about ionic compounds when you have a metal to a nonmetal. So ionic compounds are not organic compounds. It doesn't even have carbon in it. So why is propane organic and sodium chloride is not? Well, if we look at this, we go to propane. It's got a lot of carbons and hydrogens in it, so that makes it organic. Another way to look at it is it has carbon, and it's not the list that I gave you on the previous slide. It doesn't have a carbonate ion, a bicarbonate ion. It's not carbon monoxide or carbon dioxide. So it's not those few exceptions that I gave you. And then sodium chloride is not organic because by default, it's, wait, let me say that again. Sodium chloride is inorganic because it is not organic. It's kind of how we do the inorganic molecules. Okay, some properties of organic versus inorganic molecules. Now, these are just a generalization. You need to know that there's always exceptions to the rules. But if we start off here looking at organic compounds, the melting and boiling point, they have relatively low melting and boiling points. So an example is most of the melting points are less than 300 degrees Celsius. Well, you might say that that's not very low. I mean, water boils at 100 degrees Celsius, and we all know that's pretty hot. But relatively, compared to your inorganic compounds, organic compounds have a much lower melting point than your inorganic compounds. So that's what I said here. Inorganic compounds have high melting points, which are usually much above 300 degrees Celsius. If we look at the bonding, the type of bondings that happen in an organic compound is most of them are covalent, so sharing of electrons. Most of the bonding that happens in inorganic is most are either ionic or polar covalent, and then there's a few that are non-polar covalent. So your inorganic chemistry deals with kind of all three types of bondings. But if you're talking about an organic compound, that's usually mainly covalent bonds. Focusing on flammability, most of your organic compounds are highly flammable. And usually your inorganics, there's not very many that are flammable. Water solubility, mostly the organic compounds are insoluble. So for the most part, the majority of organic compounds are not going to dissolve in water. Those with polar groups, I'll talk about that a little bit later, but if you have an organic compound with some polar groups that are capable of hydrogen bonding, Now, do you remember hydrogen bonding from previously? It is when you have a hydrogen directly bonded to oxygen, nitrogen, or fluorine. So in your organic molecule, if you come across hydrogen bonding, then that makes the molecule more polar, more likely to dissolve. So there's this rule of thumb, and this is a very general rule of thumb. When you're reading through your chapter, your book is going to go a little bit more into the solubility, but in an attempt to keep this class simpler for you, we've just come up with this general rule that if your organic compound has 3 or less carbons and it contains a hydrogen bond, or it has a hydrogen bonded directly to nitrogen, oxygen, or fluorine, and has 3 or less carbons, then we're going to say that's what's going to make that particular organic molecule soluble. Okay, we'll talk more about that later. But basically, from this slide, what I want you to get is that usually your organic compounds are insoluble in water, and usually your inorganic compounds are soluble in water. And then we have the exceptions there if you don't have very many carbons and hydrogen bonds. So here is a quick learning check. Identify each characteristic as either being mostly typical of, as most typical compounds that are inorganic or organic. Okay, so A, it says that it has a high melting point. Well, that is a character that describes your inorganic compounds. They usually have high melting points. I like when I think about the difference between organic and inorganic, I actually like to think about those two examples I gave you. If you're answering a question on an organic compound, think of propane gas. And if you're answering a question on inorganic compounds, then think of sodium chloride. So is it soluble in water? Well, we all know sodium chloride dissolves pretty quickly in water. So this is going to be an inorganic compound. C has a formula CH3, CH2, CH3. Well, there's many carbons and many hydrogens, and it's not those exceptions that we went over. So this is going to be organic compound. D has the formula of magnesium chloride. Well, this is a metal to a nonmetal, so we know this is ionic. So this is inorganic. Mainly it's because it doesn't have any carbons. Burns easily in air. Well, that's testing you on that flammability. Which ones are highly flammable? That's the organic. And the last one says it mainly has organic bonds. That's the definition of organic. Organic compounds are highly, have a lot of covalent bonds in them. All right, so a little bit about petroleum. Petroleum is the primary source of the organic compounds we have. Petroleum, which is also called crude oil, is a liquid which consists of a high complex of hydrocarbons. Now, hydrocarbon is a word I want you to memorize. So I kind of wish I had it underlined here on your notes, bolded and underlined. I want you to know that hydrocarbons are compounds that contain only carbon and hydrogen. So petroleum is a mixture of a whole bunch of different variations of hydrocarbons, as well as some related sulfur, oxygen, and nitrogen containing organic compounds. Petroleum is thought to be derived from the action of heat and pressure on buried marine organisms, that over a long period of time, since there's not oxygen trapped under all the sediment, and that much heat and pressure caused the marine organisms to decompose into the petroleum and then be trapped in these underground reservoirs. Petroleum is transported from to refineries, where differences in the boiling points are used to separate it into various fractions for different uses. So what I want you to know from this slide is this boiling point, that when they separate petroleum, it's done by heating it up and then taking off the organic compounds based upon differences in boiling points. So differences in the boiling points is how they separate petroleum. Here's a picture of a refinery where they bring the petroleum to, and then they separate it up into the different fractions. This is a distillation tower. If I go back, oh, that's okay. Here's our distillation tower. So this is what happens. We've got our crude oil being pumped in. So this is where the petroleum goes. It comes into the factory and they heat it up. So they start warming it up. And what happens is the smaller compounds, those that don't contain very many carbons, are going to evaporate first. They're going to boil and turn into a vapor first. And so what they do is they collect that fraction first. So this first fraction that comes off, which is mainly natural gas, has a very low boiling point, less than 30 degrees Celsius. So you don't have to heat it up very much before your natural gas starts coming off. And then after that, they take the fraction that boils between 30 and 200 degrees Celsius. And then that part of the petroleum goes into things like gasoline. And then they heat it up. When they get up to 200 and 250 degrees Celsius, then the little bit heavier fuels like your kerosene and jet fuel come off. And they collect that and ship that out to where that's going to be used. And then you heat it up a little hotter to 250 to 350 degrees, and that's where we get our diesel fuel and our heating fuel. And you have to get it quite a bit warmer to get our lubricating oils, because those are quite a bit heavier. And then the soot that you have at the very bottom that never really boils off is where we get like our asphalt and tar. So there's a lot of different compounds we get. So these are just some examples. But what I do want you to know is that the petroleum is separated by using differences in the boiling points. Another point I guess I'd like you to know, so you could take notes on this slide, is that the fewer carbons you have, the lower the boiling point is going to be. That your lighter molecules will boil easier, and your really heavy carbon, you know, when you've got a molecule with a lot of carbons, that's not going to boil as readily. The versatility of carbon. So carbon is really unique, and carbon is the basis for organic molecules, right? So carbon is unique in its ability to form stable bonds with itself and with many other elements. So there's not very many elements that can bond to itself. You don't ever see, you know, a fluorine bonded to a fluorine bonded to a fluorine bonded to a fluorine like is common for carbon. So it can bond to itself and a lot of other elements. Because of this, there are many more organic compounds than inorganic ones. And the organic compounds are found in many different forms. So here's an example. And in all four of these examples, I just have 6 carbons. But in the first example, we have just the carbons lined up in a row, surrounded by the hydrogens. Remember when we did Lewis structures, and I told you guys that carbon is always in the middle and hydrogen's never in the middle? That's always going to be true here for organic compounds. You're going to have carbon in the middle and hydrogen will never be in the middle. Another thing to remember about carbon is it likes to have 4 bonds. So it likes to have 4, it'll always have 4 lines going to it, 4 covalent bonds coming to it. So here I've got 6 carbons lined up in a row. This molecule, I've taken those 6 carbons and I put 5 in a row and one of them coming off in what we call a branch, branching off. Here I put the 6 carbons in a ring. Here I've got the 6 carbons in a row, but some of them have double bonds and some of them have triple bonds. But do you agree that this carbon right here has 4 lines going to it? You're going to notice that's always going to be the case with carbon. This one right here, it has a triple bond and a single bond, so it still has 4 lines coming off. So carbon is always going to make 4 covalent bonds. But because carbon can do because it can bond to itself in all these different ways, we get a lot of different organic molecules. Another thing is carbon can do is bond to other elements. So here's an example of a molecule where it's got oxygen in it. Okay, I am going to take you through 3 different types of formulas: a molecular formula, a structural formula, and a condensed structural formula. And I'm going to want you to be able to know the difference between those 3. So molecular formulas tell what elements and how many atoms of each element are in the molecule. So for example, this first one here, all I know about the molecule is that it's got carbon and hydrogen in it, and it's got 4 carbons and 8 hydrogens. So it's a hydrocarbon. This one over here is a hydrocarbon, and it's got 5 carbons and 12 hydrogens. But that's all I know. It doesn't give me any indication as to how they're bonded together. So that's what molecular formulas are. Structural formulas, on the other hand, they provide more detail. They tell me not only what kind of elements are in the molecule and how many, but it tells me how they're all bonded to each other. So what you're going to notice I'm doing here with these next couple slides is I'm sticking with my C4H8 and my C5H12. Okay, so I've taken those and I've just come up with one particular structural formula for them. It doesn't have to be this one, but this is the one I've taken my C4H8, my 4 carbons and my 8 hydrogens, and I put them in a ring like this. This particular one, I decided to take my 5 carbons and just put them in a row. I could have done a lot of different things with them, but what I want you to see is that these are examples of structural formulas because I'm seeing all the bonds. What is bonded to what? Well, this takes a lot of time for a chemist because organic compounds get fairly large, and chemists don't like taking all this time showing all the bonds. So what we've done is we've come up with what we call a condensed structural formula. So it still gives us enough information to get back to the structural formula. So it provides less detail than your structural formulas, but it requires less space. But there's still enough information provided to generate a complete structural formula if required. So you can always get from your condensed structural formula back to a structural one if you want. So this right here is the condensed structural formula for if you go to the slide before where I had 4 carbons in a ring. This would be how we would do 4 carbons in a ring. The other structure I had that had the 5 carbons in a row, this would be the condensed structure. So I could get from this condensed structural formula to a structural one just by reading it from left to right. I would start off with my first carbon here, and my formula is telling me that there's 3 hydrogens on that carbon. So there's my CH3. And then I would move to my next carbon, and that carbon has 2 hydrogens. So you can see how there's enough information in the condensed structural formula to get back to a structural formula. I'm going to give you another example of that, another way you could have done this condensed structural formula. So this one here, which would be accepted. You could start off with the CH3, and you'll notice all of your chains always end with the CH3. So start off with this CH3 on the end, and then count how many CH2s you have. And this particular molecule has got 3 CH2s, so I could put those CH2s in parentheses, tell the reader that they have 3 of those, and then finish it off with that end CH3. So that's another way of writing a condensed structural formula. These ones here, where you have a geometric shape, these ones come into play whenever you have rings. When you put your carbons in a ring, then whatever the shape is that the carbons are in, you can just do a geometric shape. They're a little tricky, however, though. I'd like to just spend a little bit of time here, because what it requires is that your knowledge of carbon, that carbon always has 4 bonds. So each one of these corners of your geometric shape represents a carbon. And then they just don't show you the hydrogens because they expect organic chemists to know that carbon makes 4 bonds. So this carbon right here has 2 bonds right now. One going to the carbon on the left and one going to the carbon on the bottom. So it's implied then that there must be 2 hydrogens on this corner. And the same with these, all these corners are going to have 2 hydrogens on them. So if you're going from a geometric condensed structural formula back to the structural formula, so back to this one here, it requires you to know that carbon has 4 bonds so you can put on all those invisible hydrogens. So here is a learning check. I'd like you to expand the following condensed structural formula completely. So take it from the condensed structural out to the full structural formula, and then determine the molecular formula for this molecule. As a side note, these condensed structural formulas, when they're written like this, they're also called line structures or skeletal structures. So that's going to be important when you're doing your homework, because your homework calls for you to put in line structures, some of your homework problems. So if we are going to do this, we need to remember that every corner represents a carbon, and since they put this line out here, it must be going to another carbon. So that's kind of the first step, is to put on your carbons. And then you've got to count how many hydrogens we're going to add on. Well, this carbon right here already has 2 bonds to it. So I need to put 2 hydrogens on this carbon. Same thing with this carbon here. We need to put 2 hydrogens. This carbon has got 3 lines going to it, so it's just going to have 1 hydrogen. It doesn't matter if I put it up or down. You don't ever put it inside the ring. So it'd be kind of weird to put the hydrogen over here. I wouldn't take off points for that, but just know that this carbon needs a hydrogen on it. This carbon over here only has 1 bond, so I need to give it 3 hydrogens. Okay, but it also asks for the molecular formula. So this would be the structural formula, showing all the bonds. The molecular formula just wants to know how many carbons and how many hydrogens are in it. When you're doing a molecular formula for an organic compound, you always start with carbon, and then you go to hydrogen, and then the rule is to do all the other elements in order of electronegativity. I'm not necessarily going to grade you on that, but I do want you to put the carbon first and the hydrogen first. So let's count our carbons. We've got 3 in the ring and 1 out here, so that's a CH4. And I've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. All right, so notice this molecular formula was one that I had used in a previous example, and we had put it into the square. Anyway, so the molecular formula does not give you any idea as to how the atoms are bonded together. It just tells you what kind and how many of atoms you have. So some common bonding patterns, we've talked about this a little bit before, but in organic molecules, the carbon atoms are always going to have 4 bonds. It's usually going to be bonded with hydrogen, so you're going to have a lot of carbons and hydrogens in your organic compounds. Your organic compounds are sometimes going to contain oxygen, nitrogen, sulfur, sometimes fluorine, chlorine, and bromine. And then I kind of want to go over some of these, the general bonding patterns that we have. So carbon is always going to have 1 bond. Sorry, I said that wrong. Hydrogen's always going to have 1 bond. Carbon's always going to have 4 bonds. Nitrogen, the rest of these are usually, so I'm going to put this line here. So these 2 up here are always. Hydrogen always has 1, carbon always has 4. These 3 down here are usually. So nitrogen usually has 3 bonds. Oxygen usually has 2, and then your halogens, fluorine, chlorine, bromine, and iodine, usually you're just going to find them with 1 bond. So it's good to keep those in mind. It helps you decide, if you're doing your structural formula, how many, bonds you have to draw to different elements. So here's another learning check. Expand the following condensed structural formula completely, and then determine the molecular formula. So remember that each corner of your structure is a carbon. If it's something other than the carbon, then they've got to tell you what it is. So that's what they're telling us here, is that this upper right-hand corner is an oxygen. And then the end of this line is a carbon. So I've got 3 carbons to an oxygen, and then I have another carbon here. So you just have to go through and count your bonds. Carbon has 2 bonds, and it always has 4. So I'm going to put on these hydrogens. This carbon has 3 bonds, so I have to give it a hydrogen. I could have put it over here if I wanted. This carbon only has 1 bond, so I have to give it 3 more. And this carbon has 2 bonds, so I'm going to give it 2 more because I have to give 4 bonds to carbon. Now this is oxygen. Am I going to put any bonds coming off of oxygen? Well, if you look at the previous slide, what is the general bonding pattern for oxygen? Oxygen prefers to have 2 bonds. So I'm not going to put any hydrogens off the oxygen. Oxygen's content there with its 2 bonds. So some compounds with more complicated condensed structural formulas. We're not going to get into any that are this complicated while we're talking about organic chemistry, but when we switch over to talk about biochemistry, then we're going to start seeing organic compounds that are big and complicated, looking like these. So here is just a few, and we know they're organic because we see, if we look at this bottom right one, a whole bunch of carbon, a whole bunch of hydrogen. This one's got a few oxygens in it, and this one actually even has a phosphorus in it. So a phospholipid is found in your cell membranes. So we'll talk about that a little bit when we get to biochemistry. Here's guanine, which is found in DNA. Ribose is a monosaccharide, so it's a simple sugar. This guy here is found in the citric citric acid cycle, which you'll probably learn about in biology. Cholesterol is a lipid we'll talk about when we get to biochemistry. And here's unsaturated fat. So you can see that your organic compounds can start to get a lot more complicated looking. But I do want you to kind of be able to look at them and say, this is an organic compound compared to an inorganic compound.